Following the idea of using molecular currents to explain the formation of north and south poles, Ampere also formulated the uh, equation known as Ampere's law. So basically Ampere's law states the following: the line integral H magnetic field dot product with dl around any closed path equals I, where I is the total current, the total steady current passing through any surface bounded by the closed path. So mathematically we can say closed path integral H dot dl is equal to the current I. Now I have to specify that this is the way to write it using SI units. Now we're going to see an application of this for a field from a long straight wire. So let's talk about an application. Now, here is our long straight wire, and we're going to calculate the magnetic field that is inside this wire and outside this wire. So basically, we're going to form two loops, which are called Amperian loops. And if you have any surface that is bounded by these loops, the total steady current that passes through that surface will be equal to the line integral H dot dl. So we can use the right hand rule, so we can curl our fingers around the wire, and our thumb will point in the direction of the current, so that will indicate the direction of the magnetic field. So we can see that what we're calling dl is basically in magnitude and arc length in this circle that we're forming. So it would be equal to r times d theta if we have an angular displacement d theta. So let's apply Ampere's law for r greater than capital R and r less than capital R. So Ampere's law states that the closed path integral H dot dl must be equal to the total current enclosed by any surface that's passing through any surface bounded by this loop. Now we know that the magnetic field is circulating around the wire, so this dot product will actually give us the product of H with dl. And if you consider the magnetic field is only a function of r, at a distance r from the center, it's a constant. So therefore we will see that it is H dl, which is H integral r d theta, where theta goes from, so we can write this as r d theta, where theta goes from 0 to 2 pi. So this would be equal to h times 2 pi r. And according to Ampere's law, it's equal to I. So we find that the magnetic field is I divided by 2 pi r for r greater than capital R. So that is outside the wire. So that's one answer we have. And for the magnetic field inside the wire, once again I'm going to write the closed path integral h dl will give me h times 2 pi r, because the magnetic field will be circulating inside the wire as well, and h is only a function of r. So this will be equal to the total current enclosed. So for that I have to consider the current density J multiplied by pi r square. So what is the current density J? The current density J is I divided by pi capital R squared. So it's a steady current, and therefore I can write for this one I divided by pi capital R squared times pi r squared. So the pi's will cancel, and I will see that I also have a cancellation of r here. The magnetic field that I will calculate inside the wire will be equal to IR divided by 2 pi capital R squared for r less than capital R. So it will be increasing linearly with distance from the center, and then it will be decreasing as 1 over r. So if you wish to plot this, you would see that h as a function of r will look like this. At a distance capital R, it is I divided by 2 pi capital R, so it's increasing linearly with distance. It reaches a value at capital R I divided by 2 pi R, which is the maximum value, and then as we go away from the wire, it's going to decrease as 1 over r. So here it increases linearly with r, and then it decreases as 1 over r. So that's very simple result that we obtain using Ampere's law. Now, so let me clarify that we are considering here any surface that is bounded by this loop, and then we're considering the current that goes through this surface, and so this current inside the wire will be a portion of the total current I, because we have a current density I over pi r squared, capital R squared. So current density times the area that is enclosed by this path will give us the total current that is going through any surface that is bounded by this closed path. Now, what I would like to do is, how about in EMU CGS, or let's say CGS EMU units. How can I formulate Ampere's law in CGS EMU units? Well, so let's think about a current which is 1 ampere, a distance 1 meter, then Ampere's law tells me that the magnetic field, so I'm assuming that capital R is, let's say, 0.1 meter. So I'm outside the wire. So it will be I divided by 2 pi R. So this will be 1 over 2 pi amps per meter. So that would be the correct answer for the magnetic field at a distance of 1 meter from the center. Now, if I try to do this using CGS, I should take the current to be in amps. So 1 amp in CGS EMU units is 10 amperes. So the current that I'm considering here is not 1 amp in CGS, it's 0.1 amps. The distance R from the center was 1 meter. That means in CGS I have 100 centimeters. And the magnetic field that I calculate, 1 over 2 pi amps per meter, is how many oersteds? Well, I know that 1 oersted is 1000 over 4 pi amps per meter. So 1 over 2 pi amps per meter is 1 over 2 pi times 4 pi 10 to minus 3 oersted. So that would be H would be then 2 milli oersted, or 2 times 10 to minus 3 oersted. Okay, so having figured out these numbers in CGS EMU units, basically the magnetic field that I calculate will be a prefactor times I over R. So it cannot change, the physical dependence on the parameters I and R cannot change, but the prefactor will change. So I'm trying to calculate what this prefactor is. Okay, so I'm supposed to get 2 times 10 to minus 3 oersted as the answer. By using this prefactor alpha, a current of 0.1 amps and 100 centimeters. So this is going to give me alpha times 10 to minus 3, which will imply that alpha is equal to 2. So the correct answer is H is equal to 2I over R in CGS EMU units. So after figuring out this, basically I need to see how I should modify Ampere's law. So Ampere's law gives me the closed path integral h dot dl was equal to h times 2 pi r, and this was equal to I. So now I have to modify it. So h is equal to 2I over r. The closed path integral gives me, for integral of dl, 2 pi r. So I see that these r's will cancel, and I will obtain 4 pi I. So the correct answer, Ampere's law in CGS EMU units, is h dot dl is equal to 4 pi I. So this is in CGS EMU units. So I can edit here. I have found out that the closed path integral h dot dl is 4 pi I in CGS electromagnetic units. Here h is in amps per meter, L is in meter, I is in amps, here H is in Ørsted, L is in centimeters, I is in amps. Alright, so how about inside the wire? What is the magnetic field inside the wire? So basically what I have found that I have to replace 1 over 2 pi with 2. So also inside the wire, let's just use Ampere's law in CGS EMU. I have H times H dot dl closed path integral is H times 2 pi r. That is 4 pi times the current enclosed. What is the current enclosed? It is I divided by pi r squared times pi r squared. That is the current enclosed. So this is going to give me the cancellation of pi's here, cancellation of pi's here, and then I have cancellation of one of the r's here. So the answer that I will get inside the wire will be H is equal to 2ir over capital R squared for r less than capital R. So this was for r greater than capital R. Alright, so this was a good exercise to go in between these two units. If you remember in the previous discussion, we talked about the magnetic field outside the wire in using mixed CGS, EMU and SI units. If you take the current in amps, it was 2I over 10R outside the wire. Here we found that using CGS, EMU units, it is just equal to 2I over R. So you don't have the factor of 10 that comes from using amps instead of amps. Alright, so let's summarize what we said. Ampere's law states that the line integral H dot dl around any closed path equals I, where I is the total steady current passing through any surface bounded by the closed path. So we look at the closed path and we consider any surface, and the current going through this any surface will be equal to the closed path integral H dot dl. In SI units, this is H dot dl closed path integral is equal to the current I. Or if you use magnetic field B, it would be B dot dl closed path integral equals mu 0 I, but here we're considering H. So later on we found that the same thing is in CGS EMU units. Instead of I, we have 4 pi times I, where the current is in amps, H is in Ørsteds, and the distances are measured in centimeters. So this closed path integral, the dot product between H and dl, so if you consider a dl here, so let's do this explicitly. So I take the radial vector from the center, so I consider an angular displacement of d theta, then my dl is basically a vector that goes in between these two. So this is my, we need to stop here. This is my dl vector, which is equal to r times d theta, and it is tangential to the circle. So if you make this theta really small, it's going to become in that limit tangential to the circle. So dl magnitude here is equal to r d theta and tangential to the circle. So you can see that if you decrease this theta, d theta becomes really small. The dl vector is actually tangential. Okay, but that integral will just give me the circumference of the circle, because the dot product is h dl, since h is in the direction of dl. So here I see that h and dl are parallel to each other. So the dot product gives me h dl. The closed path integral is 2 pi r, so I find the magnetic field outside is I divided by 2 pi r, where r is greater than capital R, outside. Inside I have to consider how much current is enclosed. It is the current density times the area, pi r squared, so that gives me a linearly increasing magnetic field with distance from the center. And the direction of this magnetic field is found using the right hand rule. Your thumb points in the direction of the current, your fingers curl in the direction of the magnetic field for your right hand. So let's say this is my right hand rule. And now I wanted to consider what happens in CGS units. The conversion I can find out using a numerical example. 1 amps of current at a distance 1 meters outside a wire, let's say the radius is 0.1 meters. The magnetic field should be 1 over 2 pi amps per meter, because the magnetic field as a function of R is given as I divided by 2 pi R for R greater than capital R. And in CGS EMU units, 1 ab amp is 10 amps, so 1 amp is 0.1 ab amp. The distance of 1 meter is 100 centimeter. The magnetic field, 1 over 2 pi amps per meter, magnetic field strength. Using the conversion, 1 Ørsted is 1000 over 4 pi amps per meter is 2 milli Ørsted, or 2 times 10 to minus 3 Ørsted. Since the physics cannot change, changing the unit system, it's a prefactor times I over R, that's what I'm looking for, and that prefactor, by substituting these values, turns out to be 2. So the magnetic field is 2I over R. Therefore, the closed path integral is 2I over R times 2 pi R, which is 4 pi I. So it tells me that in CGS EMU units, Ampere's law, closed path integral h dot dl is 4 pi I. And also inside the wire, since I have found that this 1 over 2 pi factor should be replaced with so this 1 over 2 pi factor should be replaced with 2 when converting to CGS units. So if you go back to your answer here, instead of 1 over 2 pi, if you put 2, you will get 2ir over capital R squared, which is what I have verified explicitly using Ampere's law written in CGS EMU units.